We're going to go ahead and get started. Thank you so much for joining us on this special virtual edition of the MIfA Public Lecture. My name is Katie Sauer. I'm the administrator for the Minnesota Institute for Astrophysics. My role tonight is to coordinate the chat and to facilitate the Q&A with Evan Skillman. Before we get started, there's just a couple of housekeeping items I'd like to go over. Please, we welcome you to submit questions at any time during the session. Once the session is over, we'll go ahead and answer the questions as much time as there's left. Please be sure you use the Q&A function for that, which is shown at the bottom of the screen. And then the other thing is we are recording the webinar, so we plan to send the link to all the registrants following the event. And with that, I'd like to introduce Dr. Evan Skillman, who is the director of the Minnesota Institute for Astrophysics.
Thanks, Katie. It's my pleasure this evening to introduce Bob Lysak. Bob is originally from Chicago, and he got his PhD from the University of California, Berkeley, and we followed that with a postdoc position in Munich and joined the faculty here in 1982. A fun fact is that Bob is only about 10 days older than me, but he got his faculty position here at Minnesota before I even got my PhD. So, whiz kid. Bob is an expert in the theory and modeling of auroral acceleration processes, and he's been noted for his work. He's a fellow of the American Geophysical Union, a fellow of the American Physical Society, a fellow, and also was awarded the Alfvén Medal from the European Geophysical Union in 2015. Bob is part of our space physics group in the Minnesota Institute for Astrophysics, and an earlier MIfA public lecture was given by Lindsay Gleasoner on solar physics, and Bob will be talking about things that are about as close as you can get to the Earth and still call it astrophysics. The ionosphere and the atmosphere of the Earth is not usually thought of as astrophysics, but it certainly qualifies here. And Bob has two other colleagues in the space physics group here, Cindy Cattell and John Wygant, who also have done work along his lines. So without further ado, I'd like Bob to take over. Thank you very much.
All right, thank you, Evan. Am I online? I hope so. Good. All right, so let me open up my talk here. And do some other things. Oops. Okay, so I'd like you to, I guess I'll take off my mask here so you can hear me better. I'd like you to imagine that you're up north, maybe up at a lake cabin, away from the city lights. And you go outside to look at the stars, and you notice this green haze in the northern sky. And so you start to watch. It starts to get brighter, and then it starts to show structure. It starts to form into a green ribbon. As the lights get even stronger, they form thin, narrow rays that they pulsate and twist every few seconds. Sometimes the aurora forms into a large spiral that can wind up and then unwind every few minutes in this case. Sometimes then it develops into multiple auroral arcs that start to stretch across the sky from one horizon to the other. When the aurora starts to get brighter, you start to see different colors in the aurora. You see reds and blues, as well as the green, which is the dominant color in the aurora. Then eventually what happens, the aurora starts to shoot across the sky, expanding overhead. And this is what we call a substorm. If you look straight up the field line, up the magnetic field, you see these auroral rays looking sort of like a converging railroad tracks, like they're outlining a path up to the heavens. So this is something we call corona. So sometimes then the aurora will subside, and then it'll reappear. There'll be new colors, new vigor, twisting, and eventually you'll start to see vague patches in the sky, especially as you've been out out for a while and your eyes are getting accustomed to the darkness. So this is the structure that we call an auroral substorm, one of nature's most fascinating objects, and certainly the most visible manifestation of an area we call plasma physics, which I'll talk to you about tonight. So mankind has been interested in the aurora for many centuries. The book of Ezekiel describes a stormy wind which blew from the north, a great cloud with light around it, a fire from which flashes of lightning darted. The Greek historian Plutarch describes a fiery body of vast size, as if it's been a flaming cloud, not resting in one place, but moving along with intricate and regular motions. The Chinese, who are great observers of the heaven, describe an event where at night there was seen in the sky luminous vapors, yellow and white, with streamers more than 100 feet long, which brightly lit up the ground. Some said these were cracks in the heavens. The aurora over the years has inspired countless legends and myths, especially among the peoples of the Arctic. The Finnish Laplanders had many such myths, variously describing the aurora as sunlight striking the spouting of a great whale, or the great fox Ripu, illustrated here, striking the snow with his tail. In fact, the Finnish word for aurora is revontuli, which translates as foxfire. The Inuit in northern Canada described the aurora as torches lit by the honored dead, lighting the way from the warriors recently killed in battle. These northern peoples often feared the aurora, but also found it useful for traveling around in the long Arctic nights in the wintertime. Because the brightness of the aurora was, especially on the snow, was very interesting, could light up your way. During the Renaissance years, many of the great minds of European science speculated about the cause of the aurora. Descartes, Galileo, Halley, even Benjamin Franklin. It's Galileo who's credited with introducing the term aurora borealis, which translates to northern dawn, to describe the phenomenon. Auroral research took off about a century ago as mankind started to explore the Arctic and Antarctic. This is a woodcut by the Norwegian observer Fridtjof Nansen. Let's see, what do I want to say about that? This was during here one of his expeditions to the far north. In the southern hemisphere, the great explorers Robert Scott and Ernest Shackleton also observed the aurora and came up with this picture, this drawing from one of their travels. This, of course, showed that the aurora is not just the northern dawn, but also the southern dawn, which we call aurora australis. So these are some of the stories that come about. Now, the scientific expedition started largely with the efforts of Christian Birkeland, another Norwegian scientist, who endured great hardships to travel up north and to not only observe the aurora, but to make measurements of the magnetic fields produced by the aurora. In fact, even going back to Gauss, people had realized that the aurora was associated with magnetic disturbances. And that is a key to the understanding of how the aurora works. Now, Christian Birkeland, along with Carl Sturmer, his protege, developed this experiment called a torella, which was basically a vacuum chamber with a magnetized ball in the middle of it, as you can see here in the picture. And they shot particles into this device, and they saw that the particles were streamed in and lit up the ball in these two bands in the northern and the southern hemispheres. Okay, now of course, entering the space age, we can start to take pictures and study the aurora from space. So here is a nice picture of the aurora from the space shuttle. And it's a little bit dim to see, but one thing I'd like to point out, over here in this region, you can see a reddish type of aurora on top of the more green aurora. And this is due to the fact that, as we'll see, the red aurora is produced by lower energy particles than the green aurora. And those lower energy particles cannot penetrate into the atmosphere as much as the more energetic particles that produce the green. So you have this nice structure of the red aurora on top of the green arcs. Of course, even from the International Space Station, you can see the aurora. Many of the astronauts describe in great detail their observations. One thing, again, here you can also see the red aurora on top of the green, but notice here the curve of the Earth. And the aurora, as you can see from this vantage point in space, is just above the Earth. In fact, it's only about 100 kilometers above the surface. Of course, the Earth's radius is 6,000 kilometers. So it's really just above the Earth. And as Evan mentioned here, it's perhaps the closest astrophysical phenomenon that we can observe. Okay, so what does produce this auroral light? And the aurora is caused by excitation of various spectral lines in the upper atmosphere. And the upper atmosphere is dominated by atomic oxygen. In other words, just one oxygen atom rather than the oxygen molecule consisting of two atoms that we have all around us on Earth. And some of the transitions in atomic oxygen produce the light. One line, which is called the green line at 557.7 nanometers wavelength, of course, don't have to worry about that, is what we call a forbidden transition of atomic oxygen. And it's called forbidden because it usually doesn't happen in a terrestrial laboratory. Collisional effects will tend to de-excite this state before it emits light. The red color is also from oxygen. It's from a 630 nanometer line, we'll just call that the red line. And that's another forbidden transition. And as I said, this is produced by lower energy particles than the green line. The other thing to notice is that the green line has a lifetime of about 0.8 seconds for each transition, whereas the red line has a lifetime of 110 seconds. So if you're observing a very active aurora, you can often see the red light sort of trailing behind the green light. And that's an interesting phenomenon if you can observe that. There's a number of other lines, including some blue lines at 391 and 427 nanometers. Those are associated with molecular nitrogen ions. And in fact, there's lines of hydrogen, there's lines of many other elements that produce the overall auroral spectrum. So these are really the atomic physics of how this all happened. Now, all of these lines are excited by electrons, or primarily electrons, but sometimes proton precipitation in the 0.5 to 20 kilovolt range. So the question is, how do these particles get accelerated? This is where the research that we're doing comes into play. So in order to understand this, it helps to look from space. And here are two images taken at different times by different satellites. The one on the left is from the northern hemisphere. You can see the outlines of the continents put in there. This was from a satellite called Polar, which was, and this imager was flown by the University of Iowa and showed the northern aurora. On the right is another image taken in the ultraviolet. The one on the left is invisible light. The ultraviolet light was taken by the image spacecraft that was flown a little bit later than Polar. And again, you can see the superposition of the continents on top of where the auroral oval is. So the question is, why does the aurora make this pattern? Now I have a video here to show you this, and hopefully it will run. There we go. So this is again from that image satellite. I think it's the same imaging that we saw before, just showing you some of the dynamics. And this is what happens during these auroral substorms. This is what the auroral substorm looks like from space. And so we can see, and of course, this is taken over a period of many hours, as you can tell by the rotation of the Earth during this period. So we have both northern and southern hemisphere aurora that come into play. So why does it make this what we call the auroral oval? And the reason is that the auroral oval is the foot point of a global electric current system. And of course, our satellites do more than just take pretty pictures, although that's the part that most people like to see. We also put instruments on our satellites that measure electric and magnetic fields, which is the specialty of our group here in Minnesota. Other people like to measure particles and other properties of the plasma, as we call it, in space. And very early in the space age, in the 70s, two scientists from the Applied Physics Laboratory in Maryland, Ejima and Patemra, analyzed the magnetic perturbations from their satellite, which is a satellite called Triad, and they indicated that the magnetic perturbations that they saw were indicative of currents flowing up and down the magnetic field line. And this diagram is from their paper. The dark shaded line areas are regions of downward current flowing towards the Earth, whereas the sort of gray shaded lines are currents flowing up the Earth, up away from the Earth. Of course, electrons are negatively charged, so an electron moving down produces a current going up. So it's this gray region in this picture that most corresponds to the auroral oval. And so this whole structure of the magnetosphere, which produces this current system, gives us our geometry. And so here's a picture of the whole magnetosphere. The Earth is sitting here in the center. The Earth has a dipole field, which would be just like the field of a bar magnet, except for the fact that the sun emits a solar wind that, as we'll see, can push on the Earth's magnetic field. It squeezes it a little bit on the sunward side. Sun is over here on the left of this figure, and it stretches the tail, the magnetic tail of the Earth, out back like a comet. And in fact, a comet has what we sometimes call a plasma tail that doesn't proceed directly away from the sun, but off at some angle, and that's governed by the magnetic field out there. Of course, this we can't usually see because the particles that fill up this magnetosphere are not very dense, and they're not visible in general. But their electric and magnetic signatures we can observe very readily from our satellites. So we have a theory to describe this, which is called Magnetohydrodynamics, or MHD. And of course, the great scientist and cartoonist Randall Munroe, who has this website XKCD, put up this cartoon where one character is saying the sun's atmosphere is a super hot plasma governed by magnetohydrodynamic forces. And the other character says, well, whenever I hear magnetohydrodynamic, I just replace it with magic. So you can do that if you want. If whenever I talk about MHD, you can replace it by magic. But what I'd prefer you do is to replace it by music, similar word. And in fact, we might call MHD the music of the magnetospheres. And magnetohydrodynamics is, of course, there's a lot of mathematics that goes behind it, which I won't bore you with. But there's a few simple physical concepts that help us understand how MHD plasmas work. And one of them is the idea of magnetic pressure. I just mentioned before that the solar wind pushes against the Earth's magnetic field, and the Earth's magnetic field pushes back. And in fact, it deflects the solar wind out. That can happen much like a set of timpani in an orchestra can resonate at different frequencies due to the pressure inside those cavities. And I like using the timpani rather than any other sort of drum, or for that matter, a wind instrument, because the various drums are tuned to different frequencies depending on how tight the drum head is and other properties. And just like that, in different structures in the magnetosphere, we can produce waves that are like sound waves in a way, but they're not the sort of sound waves you can hear, but they're what we call magnetosonic waves, which are sort of a hybrid of magnetic and sound waves. And those can have different frequencies in the magnetosphere. The other property of MHD plasmas is that magnetic field lines can have tension, much like the tension in a string. So we can make the analogy to a violin or another stringed musical instrument. And in a plasma, we call these waves, that they're just like the waves on a violin string, we call these Alfvén waves after Hannes Alfvén, the Swedish scientist. And as you may remember from the introduction, he's actually one of the heroes of mine and I received an award based on him. But just like a violin has different strings that are tuned to different frequencies, each field line in the Earth resonates at a given frequency. And in fact, we analyze these frequencies in order to help describe the structure of the plasmas in the magnetosphere. Now, of course, unlike a musical instrument, the music that we hear consists of waves that oscillate hundreds of times per second. But the magnetosphere, being a much larger object, these waves only oscillate once every few minutes. So they're very, very low. In fact, we call them ultra low frequency waves. And as you'll see, ultra low frequency waves and alphane waves in particular play a big part in our story of how to make the aurora. So we mentioned the field-aligned current structures from Agema and Patemra. We mentioned this MHD. So how does this all fit together? Well, again, we can think of the Earth's magnetic field as a sort of a magnetic bottle trapping the plasma. Because of the magnetic pressure effect, plasma wants to be where the magnetic field is relatively weak. And so there's a couple of places where this happens. One is in the Van Allen radiation belts that surround Earth, which occur at the lowest magnetic field magnitude along the field line. Another place where this happens is in this geomagnetic tail out here, because that's also a place where the magnetic field can become very weak. And these two reservoirs, the Van Allen belts and the plasma sheet, are reservoirs of plasma that are trapped there, and that if everything was quiet, they would just sit there for a long time. Now, but the other part of MHD, the other concept, is that magnetic field lines are frozen into the plasma. Perhaps that's appropriate for a snowy day like today here in Minnesota. But what frozen in means in our case is that the plasma can carry magnetic field lines along with it. And what this means is that if we have some sort of a turbulent plasma motion in the magnetosphere, that can twist the magnetic field lines, cause them to tangle up. And electrodynamics, Maxwell's equations, tell us that twisted magnetic field lines can generate electrical currents. And so this is the association of these currents. And the alphane waves that I talk about, again, you may notice these are my favorite wave. The alphane wave can carry these twists towards the Earth and carry these field-aligned currents that we've been talking about. So all of these various processes kind of work together in order to carry the energy in towards the Earth. So then how does this all result in the acceleration of particles? Well, these twists in the magnetic field produce very strong field-aligned currents. And those currents still have to be carried by particles. Now, in a normal electrical circuit you might play with in electronics class, there's so many electrons carrying the current that they hardly even have to move in order to carry a current through, for example, from the battery to the light bulb of your flashlight. But in space, there are not that many particles. In fact, in some parts of space where the aurora form, there's only one particle every cubic centimeter, which is very, very rarefied plasma. And if the currents are too strong, there's just not enough electrons to carry that current. And in that case, we have the development of these what we call parallel electric fields. And parallel means parallel to the background magnetic field of the Earth. And so this is sort of similar, if you play around with electronics and you put a capacitor in your circuit, the capacitor doesn't carry current, but it builds up an electric field in the gap between the plates of the capacitor. And something very much like that happens in space. In fact, we sometimes call this a double layer, of at least one form of this. And those electric fields can accelerate the electrons, and that causes them to impact the atmosphere and produce the aurora. There's only one catch in this, though. If you do MHD theory and you believe MHD, it says that these parallel electric fields cannot exist. So this is a bit of a problem. But theory has to bow to observation. We do observe these sorts of electric fields. And of course, again, using some of the spacecraft that our group has flown instruments on, we can do this. Now, I won't go through this is some example of a data from a satellite called the Fast Auroral Snapshot Satellite, which is unfortunately has passed its useful life now, but it gave us a great amount of information about the aurora. I'll point out just a few things in this diagram. First of all, this top panel are these magnetic perturbations I've talked about, and wherever there's a big drop in these curves, that corresponds to the current flowing up out of the ionosphere, and where it goes back up, the current is flowing down. This red region seems it just kind of wiggles back and forth, and so what we see here in this upward current region, there we go. In this upward current region, we have this very, very bright thing. This is I should mention, this is as the satellite passes, this is a function of time, making observations. And this plot shows the energy of electrons, and the color shows how intense the electrons are at that energy. So here you can see all of these electrons are all coming in with basically the same amount of energy. And for historical reasons, we call these inverted V electrons. You can see where the energy goes up and then kind of comes back down again. It looks more like a U in this picture, but in the early observations, the resolution was low enough. It just seemed to go up and go down, and so it looked like an inverted V. Now, if you contrast this with this region over here this is going towards the polar cap. The polar cap's largely empty. There's nothing there. Here you see electrons that are a whole bunch of different energies. And notice that these are associated with these wiggles in the field. And I'd like to convince you that these particles are produced by these alphane waves that I've been talking about. So sometimes this is called the these are called alphanic electrons, and the aurora produced is sometimes referred to as the alphanic aurora. So we come up with this picture for how auroral acceleration works. The central picture here is this labeled upward current region, shows the structures. There's electric fields, and the electric field points upward in the same direction as this upward field-aligned current. That accelerates electrons down and also accelerates ions upward. Actually, those ions that are accelerated upward fill up the plasma sheet and to some extent the radiation belts. So this is the part that corresponds to the strongest aurora. In contrast, in the downward current region, we found that exactly the inverse process happens. Although the ions are not so easy to push down into the atmosphere, so they kind of go around in circles at times. So these are electrons basically being sucked out of the ionosphere, and this structure produces what we sometimes call the dark aurora or black aurora. And over here is an illustration of this polar cap region or this alphanic region, which is illustrated here by this wave going back and forth. And in this case, the electrons can actually go both up and down along the field lines. And so these are the three regions that are very, very common as we have a satellite crossing the auroral zone. And of course, this alphanic region is the region that I focus most of my attention on. Well, so we have a great story here now about what happens in the near Earth region during these things. Well, we sort of sidestepped the question of how does all this start off? How are all these things driven? And for that, just like everything in the solar system, we have to look to the sun. So here's an image. Let's see if I can get this movie going. This is an image from a satellite called SOHO, the Solar and Heliospheric Observatory. These are pictures in X-rays. You notice there's a few glitches in here. This is taken over many days. The sun rotates about once a month, so you can see the rotation here is speeded up considerably. One of the neat things about these things is you can see these loops, and these loops are actually magnetic field lines that are filled with hot plasma. Here you can see a big pile of them. This is a rather long movie, so I think I'll jump ahead a little bit here. And here you see these bright spots corresponding to these loops, and then every once in a while they flare up. They make a very bright burst of light. There you go. And all of that in her previous MIfA lecture. And there's a real big one there. That was a really nice, nice blast of a solar flare. So this is the sort of thing sort of activity that happens in the sun. But actually, sorry, Lindsay, but the X-rays from these flares are not the thing that's most effective at driving the particles in the aurora. But associated with that are these bursts of plasma that mass ejection, because they come from the corona of the sun. Let me explain this picture, which is also from SOHO. This little circle here is where the sun is, and it's being blocked by a disk on the satellite. On Earth, you can't do that very well because the scattered light comes into your eye. But in space, you can block out the sun very nicely. And what you're seeing are electrons that are scattering the solar light that you usually can't see, except maybe during a solar eclipse. You can see this sort of thing. Even then, they're pretty dim. But these are what carry all of the mass. And this is these coronal mass ejections. As a reference, I looked up on the web that a fully loaded supertanker, some of the big supertankers that we have about 10 to the 9th, a billion kilograms. So the mass is ejected from these coronal mass ejections is like 1,000 supertankers. So it's a massive amount of mass, so to speak. I should mention that these travel at a few thousand kilometers a second, faster than the normal solar wind, which is usually about 400 kilometers a second. And they take a couple of days to get to Earth. And that's important because that means that by monitoring the sun, we can start to get some indications of when we might be able to see aurora. Of course, the sun, as you may know, undergoes this so-called 11-year sunspot cycle. And here's some nice images from a different satellite, Yoko, which is a Japanese X-ray satellite, showing an image of the sun every year from 1996 to 2006. And 96 was a period of solar minimum, very, very smooth sun. And then you start to see all of these bright active regions building up and building up until about 2001 was the solar max at that point. And then things tend to fade away and go back to being quiet. Right now, this was a previous solar cycle. Right now, we're right about here at the 96 part. We're just coming out of the solar minimum. And the number of sunspots and the amount of solar activity is beginning to ramp up. And so in about 4 or 5 years, we should be at the solar maximum period where there's stronger solar activity. That's pretty important, especially for us here in Minnesota, because you go up into Canada or Alaska or northern Scandinavia and you can see aurora almost every day if the sky is clear. But here down at middle latitudes like Minnesota, it requires a very large amount of solar activity in order to push the aurora further south so that we can see it here. So you're much more likely to see an aurora if you go out 4 or 5 years from now than if you go out tonight, especially in Minnesota, of course, because it's totally cloudy here tonight. All right, so that's what's happening to the sun. What happens, how does this make aurora? Well, I mentioned this idea of magnetic pressure, and that magnetic pressure from the CMEs can hit the Earth's magnetosphere. It can cause all of these oscillations, these drums and violins that we were talking about before, shaking up the whole magnetosphere and generating these field-aligned currents. What happens here is that in the tail, the magnetic field lines can undergo a process we call reconnection, which causes the magnetic field lines to collapse. And I should mention there's some controversy about this subject. Some people think of reconnection as being the prime cause of everything. Some people think it's what happens as a result of other processes going on. But nevertheless, it's pretty clear that the tail does in fact collapse like this during these events. So when that happens, the plasma that's been stored in the tail gets injected towards the Earth. That generates alphane waves, it generates field-aligned currents, and it also provides particles to be accelerated into the atmosphere to produce the aurora. So there we go. And so we call this process a magnetospheric substorm. as opposed to the auroral substorm I mentioned before. So this is sort of the magnetospheric counterpart of what's going on in the auroral zone. So I have here another movie. Again, this is also from NASA. This was a movie put together by a satellite project called Themis, which put 5 satellites into the right position to observe these substorms. And this first image shows the orbits of those satellites. And this is a simulation using the equations of MHD to describe the magnetosphere. And what you can see here is that every once in a while, and I'll do this one again as well, every once in a while, the tail will collapse, the particles will come in towards the Earth, and then what we call a plasmoid will be ejected out the tail, out into space. So here's the black lines are the field lines, and here you see them kind of coming in, collapsing, boom, and there goes the plasmoid out into the tail. So these are the sorts of structures that we can observe now using our satellites. Well, that's all fine for the Earth. What about other planets? Jupiter in particular also has aurora. And in fact, Jupiter's auroral emissions are very interesting and sometimes in some ways similar and sometimes dissimilar to the Earth's aurora. In fact, other planets, Saturn, Uranus, Neptune, all have auroral processes. Even Mars has some weak little auroras because Mars doesn't have a big magnetic field like we do, but some of the rocks on Mars have what we call remnant magnetism, they actually make little mini magnetospheres, and auroral type emissions have been seen from that on that planet even. But Jupiter is of course, as in most things in the solar system, the biggest and the brightest of these auroras. This is actually a picture taken from the Hubble Space Telescope by colleague John Clark at Boston University. So the interest in Jupiter's aurora has been enhanced in the last few years due to a mission that's called Juno. And we've sent a number of missions to Jupiter in the past that you may have heard of. But Juno is the first satellite to go into polar orbit around Jupiter. And in fact, it's a very extreme polar orbit, as you can see in this diagram. And in fact, it comes very, very close to Jupiter. It comes within 5,000 kilometers of the cloud tops of Jupiter, which is only 7% of the radius of the planet. So these are all very, very, very close, the closest approaches to Jupiter that we have ever made from a satellite here. And of course, part of the mission from Juno is to map out the gravitational fields of Jupiter and map out the magnetic fields of Jupiter. But this polar orbit is ideal for looking at the aurora. I'll just show you some neat images. These don't have much to do with the aurora, but these are some of the images of atmospheric turbulence that can be associated with Juno and its satellites. And so here's this picture of Jupiter's aurora again. And the interesting thing here is that at Earth, the aurora is mainly driven by the solar wind, and as we've been talking about. But at Jupiter, there's 3 different ways that aurora is produced, we think. This polar region up here we think is associated with the interactions with the solar wind, just like it is at Earth. Of course, the solar wind's a little bit weaker by the time it gets out to Jupiter, so these emissions are perhaps weaker than at Earth. But what's called the main oval at Jupiter, which goes all the way around the planet, is thought to be associated with the very rapid rotation of the planet. Now, Jupiter in diameter is 10 times bigger than the Earth, but it rotates once every 10 hours, more than twice as fast as the Earth does. So since the magnetic field lines are frozen in, as I mentioned before, the magnetic field lines are whipping around every 10 hours. And as you go further and further out, eventually they just can't keep up. And that causes bending and twisting of the field lines. And bending and twisting of the field line is associated with field-aligned current and all of these auroral processes, which are somewhat similar to what happens on Earth. But in addition, one thing that we don't have is you see here, it looks like actually a little comet on Jupiter's aurora. It's got one bright spot and a little bit of a tail. This bright spot is on the magnetic field lines that are connected to the moon Io. And you may remember Io from the pictures. This is sometimes called the pizza moon. It's the one that has all the volcanoes that can spew off gas that can get ionized and make plasma. I'll talk a little bit more about that. Ganymede and Europa, two other moons of Jupiter, also have these type of emissions, although not as strong. So you might ask, why doesn't our moon do anything like that? Well, the reason is that our moon is pretty far away. Our moon is 60 times the radius of the Earth from the surface of the Earth, whereas Io is only 6 times as far in terms of Jupiter's radius from there. So Io and Ganymede and Europa are right in the middle of the magnetosphere, whereas our moon is just passing in the far distant tail of the magnetic tail of the Earth. In fact, our moon spends a lot of its time in the solar wind itself, not even in the magnetosphere at all. So this is the idea here. And so I'll talk a little bit more about Io, which is interesting. So Io spews off all of this plasma. It makes what's called a plasma torus around Jupiter, which can be observed here in some spectral line. I'm not sure which one it is. And then, as I said, Io is also associated with this magnetic flux tube, and a planet or moon like Io that's moving through the plasma acts like a generator, can generate field-aligned currents. So that generates currents, and of course alphane waves always go with field-aligned currents, and this produces these bright auroras. Actually, that tail that we were talking about is thought to be due by the fact that these alphane waves bounce back and forth between the plasma torus and the surface of Jupiter and produce this extended tail. And these are the sorts of things that we're studying with Juno right now. Okay, so that's the story at Jupiter. Oh, I did want to mention one other thing about Jupiter, and that is that at Earth, I mentioned that this type of aurora where all the particles come in with one energy is really dominant, and that broadband alphanic aurora is somewhat weaker. Jupiter seems to be the other way around. This alphanic type aurora at Jupiter is often the dominant structure, and we see a lot of different types of particle distributions that I don't have time to get into that are associated with that. But of course, what probably many of you want to know is, when should we go out and look at aurora? So, of course, maybe this is obvious, but the sky has to be clear, no clouds, and dark, away from the city lights. Although a really bright aurora can be seen even from the city. One reason I stay here for 40 years almost is that the first week that I arrived in Minneapolis to take on this position, I saw aurora from South Minneapolis, right in the middle of the city. And I said, okay, I'll stay here. I think this is my place. But if you really want to see aurora good, it's best to go up north. Go up to the North Shore or the Boundary Waters, which are some of the best auroras that I've ever seen have been while doing ski trips up in the Boundary Waters. The other thing, as I mentioned earlier, is that we have a couple of days leeway that one of these coronal mass ejections might be coming towards Earth. And so various websites, and my favorite is called spaceweather.com, pretty easy to remember. They will give you information about when auroras are coming. In fact, they'll even call your cell phone if you want to tell you there's going to be an aurora. So that's a very useful resource to find out what's going on. Another aspect of this is that the auroral activity tends to peak near local midnight, because that's the part of the magnetosphere that's connected directly to that magnetic tail. And so you can see auroras anytime. Don't quote me as saying you can only see them at midnight, but that's really when the activity is usually the strongest. So it helps if you really think there's going to be aurora. It's good to stay up late and try to find it. As I mentioned before, the aurora reaches more equatorial latitudes at solar max. So for us at mid-latitudes, this is an important concept. The next solar max is predicted to occur in about 2024, 2025. It's as a lot of these things in space, it's rather irregular, so you can never be quite sure how that's going to work. But people have a pretty good confidence in that prediction. Another thing that's often quoted and is somewhat harder to understand is that the auroral activity peaks near the equinoxes, near March and September. And nobody quite knows why. It may have something to do with the fact that then the Earth's axis is tilted sort of sideways to the solar wind. And so the solar wind comes in at a different angle than it does. And depending on the angle between the Earth's magnetic field and the solar wind magnetic field, the effectiveness of the CMEs hitting Earth can be enhanced. So you'll often hear people say, "Oh, well, it's Aurora season," as March or September comes by. But you know, that's again it's not very predictable. So to summarize, here's what we've been talking about. I hope you can understand now that the aurora is a result of the complex interplay between the sun and the Earth's magnetosphere. Solar activity perturbs the magnetosphere, causing the tail to collapse and eject these particles towards the Earth to make the aurora. They're accelerated by those parallel electric fields, either in the static case or those associated with the Alfvén waves, and they can impact the atmosphere, producing, oops, I'm misspelling there, but producing the aurora. Now, one thing that I always like to mention in these talks is that some people, even including NASA, have put out a statement like this, that particles are blasted from the sun. Some plunge through Earth's magnetic field and make bright northern lights. That's true up to a point, but that's only about maybe 10% of the auroral light that we see. Most of the aurora comes from the plasma that's been trapped in the radiation belts and in the plasma sheet in the tail that are released when these coronal mass ejections basically shake up the magnetosphere and shake those particles loose. So that's something that, of course, it's a lot easier to say particles from the sun just come in there, but the situation is a little bit more complex than that. So that's basically what I wanted to say. Thanks for your attention, and we'll take any questions at this point. Oh, yes, that's right. I did want to put this one up here, that we have, of course, the Institute for Astrophysics here at Minnesota has very active programs in this sort of outreach, and you can catch stuff. There's this, what we call Universe at Home, and there's a number of series, including one tomorrow, and that you can find here on YouTube. And in addition, of course, on our website, at this Universe at Home, you can see more of the future events coming up to play.
Okay, Bob, thanks. Oh, should we clap here?
The 3 people in this room can clap.
Very good. We have some great questions. I've been previewing them here. And the first one is my favorite. It says, Bob's great nieces say good luck and they miss him. But the first...
My nephew said that the old one might last 5 minutes and the younger one probably 1 minute.
Very good. Okay, so the first one is the aurora is a visible eye phenomena. What do instruments pick up about it for the ultraviolet and infrared portions of the spectrum?
Well, some of those images I talked about were in the ultraviolet. The aurora, of course, does not an Earth's aurora is not so much infrared, but there's quite a bit of ultraviolet from these. In fact, even X-rays from the higher energy particles. At Jupiter, there is quite a bit of infrared emissions in the aurora. And of course, our satellites, of course, just like all the astrophysical instrumentation that we have that study, everything from the Earth to the universe as a whole, we observe that in many different wavelengths, and the same is true for the aurora.
The next question is, when the aurora is strong at the North Pole, is it typically also strong at the South Pole at the same time?
That is a great question. In fact, that's something that we are actively pursuing. It seems to be the case for the most part. As you might expect, if these things are coming in the tail, it might go to the north or the south. But of course, the Earth has the Earth's magnetic field is tilted, and sometimes things happen a little bit stronger in the north than in the south, or vice versa. But there's no particular reason why north is always brighter than south or anything like that. And of course, looking at some of these images, of course, most satellites can't look at both north and south at the same time. But now we have enough satellites up there that we have satellites in looking at the two hemispheres at the same time. We see some of the same structures, but they're not always in the same place, and they don't always move quite the same way. So it's a very active area of research at this time. Yeah.
The next question is, do the ultra low frequency waves have harmonics?
Yes, absolutely. And in fact, one of the ways that we use those ultra low frequency waves is something we call magnetoseismology, which is like the seismology that they use for earthquakes, except for measuring magnetic fields. And it turns out that, you know, in a violin string, there's the harmonics are pretty much, at least idealized, they're pretty much multiples of the fundamental. That's not quite true in the Earth's, for these Earth's magnetic field lines. You could think of it as a string that's, a violin string that's heavier on one end than on the other. And so the waveform isn't exactly the same as it would be if it was a uniform string. So by understanding how the harmonics go, we can try to fit that and try to make a model for how the plasmas are distributed through the magnetosphere. That's one of our issues here, is that, you know, the magnetosphere is a huge place, and we put up these satellites that, you know, they may be as big as this room, but on the scale of the magnetosphere, they're very tiny. And so we're making only very few measurements. So these sorts of waves can help us give a sort of a global measurement of the plasma distributions in the magnetosphere.
The next question is, does the pattern of the magnetic current affect the color/look of the aurora?
I would say the pattern of the current doesn't so much matter. What matters for the color, for the most part, is the energy of the particles that are coming in and the number of particles that are coming in. So for example, the green line is thought to be directly proportional to the total flux of energy of these particles coming in. Whereas, for example, as I mentioned before, higher energy particles tend to make the green and blue lines, lower energy particles tend to make the red. So the energy of the particles is largely determining the color.
This next question came in anticipation before you talked about this, but it said, do the twisted plasma fields generate electrical energy like a generator?
Exactly. It's exactly the case. In fact, I hate to bring this up because it's a total misuse of it, but if you've seen the movie The Hunt for Red October, they talk about the submarine being run by a magnetohydrodynamic generator. And actually, such things exist, although I don't think they would work in the ocean. But in a plasma, if you pass a plasma between two plates, the positive particles deflect one way and the negative particles detect the other way, so they can charge up the plates, which can then discharge as a current. So that's what we're talking about here.
All right, the next question, in the CME video, what is the dark band from?
The dark band, I'm not quite sure. Maybe I'll go back to look at that, if we can find it. This dark band here, I guess you're talking about. I think actually what that is it's a little rod in the satellite that's holding this little disc here. So it's actually something on the satellite, not something that's happening in the sun. Very good question. I never thought of that before.
Yeah. Okay. Does aurora season peak at both equinoxes in both hemispheres? Does one peak favor the southern hemisphere and the other peak favor the northern hemisphere?
I don't think that there's a preference that way. I think, of course, at equinox, of course, almost by definition, things are pretty much the same between the northern and the southern hemispheres. So I can't say that I know of any study actually that specifically has talked about that point, but I would guess that they're equal between March and September. And I do have to be careful because I do have colleagues that work in the southern hemisphere. So we don't talk about spring equinox or fall equinox. We talk about March or September equinox. Yeah.
Very good. All right. This one ends in a little disappointment here. It says, which country area would you suggest to travel to for the best option for finding the aurora? And then parenthetically, it said Iceland in February proved fruitless. Really?
Oh, that's too bad. I would have thought Iceland in February would be pretty good. Maybe March. Maybe that would be better. I know, like in fact, on that website that's called spaceweather.com, there are advertisements for aurora tours some of which, a lot of which actually come from a town in northern Sweden, actually, that I visited last year called Tromsø, which is on the north coast of Norway. And so there are people that will take you out and drive you around the countryside until you find the aurora. But it can be hit or miss, because if the sky is cloudy, you know, unless you get into an airplane and get above the clouds, you can't see the aurora. So going north, and like I say, I'm disappointed that, as you are, that you didn't see aurora in February in Iceland, because there's been some fantastic aurora. In fact, I remember, you might remember a few years ago, there were these big volcanic eruptions in Iceland, and there were some fantastic pictures of volcanic plumes superimposed on the aurora, which was kind of a nifty sight. But if you go up north, again, North Shore, up into Canada, Alaska, Scandinavia, or Antarctica. I mean, you can see good aurora in Antarctica if you want to spend the whole winter there, which some people do. And but getting away from the lights is the most important thing.
So maybe it was just a bit of bad luck there? Or,
I would say it's bad luck.
but it would also matter where you are in the solar cycle too, right?
That's true too as well. But also, when you get further and further up north, the solar cycle doesn't matter quite as much as it would at mid-latitudes like here in Minnesota.
Okay. Is it possible for an aurora to create light that we normally can't see?
Well, yeah, I mean, we were talking before about ultraviolet and infrared emissions. And the other thing that I didn't mention before is that the aurora also produces radio emissions. There's radio waves that actually, because of the ionosphere, we can't see those very easily from the Earth because the ionosphere filters it out. But if you go out into space, in fact, there's a type of radio emission called auroral kilometric radiation, because its wavelength is about 1 kilometer, that has been associated with the aurora at Earth. And in fact, that's also been associated with the aurora at Jupiter, although it's at a somewhat smaller wavelength at Jupiter because it's higher frequency.
Okay, I think you're going to love this question. What is the physical mechanism driving magnetic reconnection, and why is it controversial?
Very good question. I'll get in trouble with my colleagues in the group because we have some disagreements about this. The reason is that magnetic reconnection is a process, again, that is forbidden by MHD. So we don't expect it to happen in most cases. Now, that all being said, some of the controversy is not that it happens, but what role it plays. Now, most recently, we've gotten a lot of new information on magnetic reconnection from a satellite mission that NASA has put up called Magnetospheric Multiscale, or MMS for short. And MMS has 4 satellites that are flying very, very close together within like kilometers of each other. Of course, satellites are much smaller than that, so they don't run into each other. But when you get magnetic reconnection involves a violation of MHD in a very, very small region that's hard to catch, if you will. So until MMS, we never really had really good convincing evidence of how magnetic reconnection took place. But as I say, the fact that it exists is perhaps not as controversial as its role in the whole substorm process.
Okay, this next one is just, I think they want you to return to this thing, is does Mars experience aurora? So maybe you can.
Yeah. What happens on Mars, of course, we've had a lot of satellites that have gone to visit Mars now. And presumably in older days, Mars did have a magnetic dynamo that produced a field like the magnetic field of the Earth. And what happens is that as rocks cool, particularly rocks containing some iron or other ferromagnetic materials, when they cool past a certain temperature, which is known as the Curie temperature, they maintain their magnetic field. The magnetic field gets frozen in, to use the same term that we've had. So some regions, particularly in the southern hemisphere of Mars, have a number of these rock outcroppings. And they have observed things like, well, they've observed alphane waves and some emissions. Of course, they're very, very weak and hard to see at Mars, but they probably exist, and they exist in these small remnant magnetic fields.
The next question, are aurora most intense at the magnetic poles or some distance away?
Well, some distance away. And the reason for that, the auroral oval, roughly speaking, you know, the Earth's field is more like, in the inner part is more like a dipole, and then all of this stuff about the tail and how it gets stretches happens further out. And the auroral oval tends to be more or less at the place where the transition between this dipole-like field and this more tail-like field takes place. And so generally, in terms of a latitude, the aurora tends to take place about 20 degrees of latitude further south than the geomagnetic pole. And of course, it's centered on the geomagnetic pole, not on the geographic pole, which of course is another story. Yeah.
Okay, we have a question from Seattle. You gave the best time to see the aurora in Minnesota. Would it be the same time of year for the West Coast?
Yes, but the problem is that, again, I mentioned this magnetic pole that the auroral oval is around. Magnetic pole is more or less straight north of Minnesota, you know, up in the Canadian islands. And so in the West Coast, in the lower 48 at least, in Washington State or Oregon, they're further away from the pole and further away from the auroral oval than we are here in Minnesota. So it would take a stronger magnetic storm to get the aurora down there. Now, as Evan mentioned, in the introduction, I went to grad school in Berkeley, and we almost saw an aurora one time from Berkeley, even from California, but we didn't really quite see it very well. But there was claims that the aurora was visible as far south as that. In fact, there's even been claims that the aurora has been seen as far south as in Cuba during some very strong storms. But the things about solar maximum and being a dark night and being around midnight also apply on the West Coast as they would here in the Midwest.
And also the thing about weather.
And also the thing about, yeah, that'd be the biggest problem I would guess in Seattle. Sorry for you. My best graduate student is from Washington State, so he said he misses the rain, I suppose, especially now that it's snowing here.
All right, next question. What do you think would happen to the aurora during a reversal of Earth's magnetic field?
That's an excellent question. The answer really is no one knows, because we have not performed this experiment. And part of the answer to that depends on how the Earth's magnetic field reverses. So if you think about this, it could happen a couple of different ways. One is that if you think of the Earth's field as being associated with a dipole like a bar magnet, that bar magnet might just rotate and more or less keep the same magnitude as it goes along. In which case, the auroral oval would more or less follow along with it. Might be a little bit different depending on how close you were to the sun. But the other case is that the magnetic field actually disappears and then grows again the other way. And so if the magnetic field basically went to very small values, we might not really see the sort of structured aurora that we would see. Particles would still hit the atmosphere, but the effects of the magnetic field to accelerate the particles wouldn't be present really in that sense. And in fact, the same sort of green light that we see in the aurora is, if you have very, very sensitive instruments, you can see is what's called the air glow. And that happens all over the surface of the Earth. So I think if the Earth's magnetic field totally went away, you'd probably see some effect of this air glow. Although, of course, most of that would be on the day side where the sun is. And of course, in the sunlight, that's going to wash out most of any of that. So it would be very boring for an auroral physicist if the Earth's magnetic field went away.
All right, the next one's a little bit long. I don't want to mess this up. So thanks for the great lecture. If the aurora is strongest at the collapsing magnetic fields, then how does that correlate to the poles where it is most visible, as opposed to the opposite position of the Earth related to the sun's position?
Well, let me go back and show this picture of the magnetosphere. I can use that to explain. Oh, there it is right there. I have a bigger one here, don't I? There we go. So over here is the plasma sheet. See, the Earth's field, again, as I mentioned, is more of a dipole in this inner part. So the field lines that connect to this plasma sheet, as you can see, this PSBL stands for plasma sheet boundary layer, where a lot of this action happens. That comes in and the field lines that are connected to that come in like so and hit the Earth in this region around the auroral oval. So that's the magnetic field line makes the connection between the dynamics in the plasma tail and the acceleration of particles in the aurora.
The next question, where do the particles in the plasma of the radiation belts, for example, the Van Allen belt, come from?
Yeah, another good question. There's a mixture of plasma coming from the solar wind and also plasma coming, as I mentioned before, the upward parallel electric field accelerates downward, can accelerate ions like protons and oxygen ions upward. Now, the tricky thing is that if you look at the most common ion in the magnetosphere is a proton, just a hydrogen atom without its electron. And a proton can come from anywhere. You can't really tell where that comes from. But another major constituent of the magnetosphere is oxygen. And the oxygen coming up from the ionosphere tends to not be very strongly ionized. It's maybe only lost 1 or 2 of its electrons. But whereas the oxygen that's coming from the solar wind has been through the hot corona where temperatures are 1,000,000 degrees, and those oxygen ions are usually stripped of up to 6 of their electrons. So they have a different charge than the oxygen coming from the ionosphere. And so using the oxygen as a tracer, scientists have been able to determine that a bulk of the plasma actually comes boiling up from the ionosphere, and a minor part, I don't know if you would say 10 or 20%, I don't know the exact number, would be coming from the solar wind. So those are the 2 main sources at Earth. And of course, as I mentioned, at Jupiter, we have the additional source of the particles coming from the moon Io. So that complicates things again, even more.
So the next question is, have aurora been duplicated or studied in the lab?
To some extent, yeah. Well, in fact, there's Torella experiments that I talked about earlier were very early experiments that have done that. Other experiments have tried to do similar things. More recently, a lot of the attention has tried to focus on doing laboratory experiments that can illustrate some of the individual processes that produce the aurora. So for example, as I mentioned, Alfvén waves are my favorite wave in the universe. And at UCLA, they have a large, what they call a large aperture plasma device, which has the acronym LAPD, which I'm sure they're amused by. That is a long, I don't know how long it is. I think it's about 30 meters long or so, that is long enough to contain these Alfvén waves. And that's part of the problem with lab experiments is the scales in the magnetosphere are huge. And to reproduce that in the laboratory is something that's somewhat difficult to do.
Now a question about the Earth's magnetic field. Is the axis of the Earth's magnetic field changing its orientation?
Yes, that's also true. It's not like the geographic pole that would be the pole that the Earth spins about, because the magnetic field changes quite a bit. And the thing that's intriguing about it is that there's 2 things you might call the magnetic pole. One is if you tried to fit the Earth's magnetic field to a dipole, you could say, well, where is the axis of that dipole? And so that's what we sometimes call the geomagnetic pole. The other thing is that as the Earth, in the dipole field, the dipole field lines kind of come like this. Right at the pole, the field lines should come in exactly vertically to the surface of the Earth. And this is sometimes called the dip pole because it's where the magnetic field dips. And that pole is much more active than the other version of the pole, depending on the actual dipole. And of course, it's the first one. It's that dipole that's mostly concerned with the aurora. There was a bit of news a few months ago that this dip pole actually has moved away from Canada and crossed over the international date line into Siberia. So it can move quite a bit. And the other thing, and going back to the question about reversal of the Earth's magnetic field. In the last 100 years or so, the Earth's magnetic field has decreased by the number I remember is that at the rate that it's decreasing, we would lose the magnetic field in something like 1,000 years. So some people have said, well, maybe we're at the beginning of a reversal of the Earth's magnetic field. 1,000 years is nothing geologically. You know, the time scales of the Earth are millions of years and billions of years. Yeah, so that's.
So is it appropriate to say the magnetic pole wanders?
The magnetic pole does wander, yes. That is the word you're looking for. Okay, yes. And of course, the reason behind that is the fact that all of this stuff is happening in the core of the Earth, where there's also magnetohydrodynamics is used to describe all of this. But of course, we can't do experiments down at the core of the Earth, at least not in real life. In some science fiction movies they have. But since we don't really know what's happening in the core of the Earth, it's hard to predict how the Earth's field is going to vary over longer terms.
All right. Are there potential dangers to aircraft, spacecraft, or other airborne devices from the aurora?
Oh, I hope not. Well, one of the things that's not a particular danger, but is a nuisance, is that the aurora disturbs the ionosphere, and the ionosphere can is used in communication. You know, we bounce radio signals off the ionosphere, and this is often used by aircraft, for example. And so if the communication goes out, that could be a problem. I think that the more pressing issue for people flying in airplanes, and that is the fact that when you get up above the Earth's atmosphere, the amount of radiation, direct radiation from the sun, becomes bigger, and that's the thing that's concerning to people, for example, like airline pilots. So when there's a big strong magnetic storm, they actually put out alerts to the airlines, and in some cases they'll, some of these, especially these routes that go from over the pole from one continent to another, sometimes they'll choose to take a more southerly route when there's strong activity, which is going to be associated with enhanced radiation from the sun.
Is the aurora expected to occur during the daytime? Would it have different behavior on the sunlit side of the Earth?
Well, of course, if you mean the aurora is something you see, you can't see it. But it's actually a really good question, because our instruments could tell whether those particles are still hitting the atmosphere. And there have been some studies that have suggested that the aurora is in fact suppressed in daylight. See, part of the issue with how the aurora evolves is the conductivity of the ionosphere, the electrical nature of the ionosphere, which is much different in the daytime as it is in the nighttime. And it's thought by some people, and I think there's something about this, I'm not sure, I'm totally convinced, that the aurora is suppressed in daylight. And even if we could see it, it wouldn't really be there. Yeah.
Next question is, with the current change in the Earth's climate, is there any change in the aurora borealis?
I don't know of anything directly. Now, one of the things that relates to that, not the aurora directly, but solar activity is thought to have some effect on the climate. Part of this is due to the fact that in the 1600s, back in the old days, even before my time, there was a period in Europe that was called the Little Ice Age. And because things were colder, you think of Hans Brinker and the Silver Skates, people skating on the canals in Holland and all this sort of stuff. And that happened to correspond to a period where there were very few sunspots. And so some people have speculated that an enhanced solar activity is responsible for some of the variation in the weather. No one has yet come up with a mechanism for that that's convincing, to me at least. And so I think it's probably, I would say it's probably a much less of an effect than the anthropogenic effects that we all worry about these days.
Next question is, why does the disruption of the magnetic field not have a significant impact on magnetic compasses on the Earth?
Well, of course, most of the compasses that you would use for, for traveling around while you're backpacking are not all that sensitive, but it does. These fluctuations are observed by sensitive magnetometers. And so we do measure those fluctuations. Now, even the strongest fluctuations at the surface of the Earth are usually less than 1% of the magnitude of the magnetic field. So when you go further away from the Earth, that situation changes. The magnetic field gets much weaker, and these currents make a bigger effect. But yeah, you should basically think of these at the surface of the Earth. These are producing a 1% or so effect.
So this is just, returning, I think, to this, and you can answer or not, is does the climate change have any effect on Aurora? How is it expected to change? Maybe you felt you've answered that already, or so.
Yeah. I can't really think of a real strong mechanism. Remember, all of the climate is primarily in the lower levels of the atmosphere, below something like 10 or 15 kilometers, which is called the troposphere. And the aurora is taking place at 100 kilometers up. So there's a big gap in between those. So while I wouldn't totally rule out the possibility that there could be some connections there, because on a general principle, all of these things seem to be connected in some way or another, but there's no real direct connection that we know of these days.
And do CMEs happen throughout the year?
Yes, CMEs can happen basically at any time. They can happen, of course, they're governed by the solar cycle. There are fewer of them during solar minimum than during solar max. But even in solar minimum, you can have a random CME come out and cause trouble. So it's the solar cycle is really the more important effect in there.
If the Earth's magnetic fields disappeared, would it present dangers to life on Earth?
Yeah, very possibly. I mean, because then the magnetic field produces this shield for these charged particles that are coming in from the radiation effects that we have, and it's probably an experiment we shouldn't really think about doing. But actually, we have to think about this, because if we're thinking about sending people to Mars or even to the moon, because the moon, as I mentioned before, spends a lot of its time out in the solar wind, they're going to have to be shielded against those solar particles coming in. And in fact, I think this is one of the biggest challenges to actually sending manned missions to Mars, is providing enough shielding for the astronauts to protect them from the solar radiation that's coming out, particle radiation.
All right, here's a follow-up. Could a long-term weakening trend of the aurora be a predictor of a magnetic reversal?
Could be. It's a very subtle thing. It's taking place on very long time scales. As I mentioned before, the magnetic field itself is being reduced by a not trivial amount, and that's going to have effects on the aurora. So it could definitely have some effect, but I'm not quite sure how much.
And here's one: was the aurora stronger when the sun was younger?
Oh my gosh. I don't know. We didn't have our instruments around to measure it back then. So I think that's a harder thing to answer. But actually, it does have some relevance, because now, of course, we've discovered many exoplanets traveling around other stars. And presumably, some of those planets may have auroras. And if we could start to observe some of those, and in fact, the radio emissions from the aurora are something that some people think might be the first signature of aurora on an exoplanet. And of course, if we could come up with a catalog of different exoplanet auroras and how they interact with their various stars, we would understand quite a bit better how all of this works. In fact, that's one of the nice things about having good instrumentation at Jupiter now, is that by comparing Earth and Jupiter's aurora, we can learn more about each of them.
And so 10 to the power 12 kilogram of plasma was mentioned.
Yes.
What are the mass components, and does this disperse on a spherical front?
Well, it usually comes up kind of as a bubble. I mean, actually, the picture that I showed, let's see, where was it again? You can kind of see the structure, how it kind of comes out as a bubble. Oops, there we go. So over here, you can see this big blob of plasma coming out. You can see it's almost like it's still connected to the sun in some ways, and then eventually it blows out. So it's not just spherically coming out all directions at once, but it does have this kind of shape. Actually, sometimes people look for for these coronal mass ejections that appear to be symmetric around the sun like this, because that might indicate that one is coming right at us. See, this one that's shown in this picture is going off in some different direction, far away from Earth. So that one wouldn't be one that would impact us here.
And now you triggered something with the extrasolar planets. From an exobiology perspective, would a strong aurora on an exoplanet be an indicator of the presence of oxygen and thus life?
Well, if you saw the same spectral lines, then that might be true. Now, the oxygen that we see in our aurora is from our aurora. I mean, at Jupiter, for example, actually, at Jupiter, the aurora is a little bit more boring as far as the colors go, because the Jupiter is a gas giant made mostly of hydrogen, and so there's a limited amount of spectral lines that can be observed. So the presence of oxygen isn't necessary for the aurora, but it is for the sorts of aurora that we see at Earth.
All right. The last question here is actually a comment thanking you for the lecture, which I'm sure all the participants would like to share in that.
You're very welcome.
And then talking about their amazing views of these things, that they saw aurora that were just above the horizon and directly overhead and all over the sky, and they're very excited about that.
No, it's really, yeah, actually every time I give a lecture like this, I get a lot of stories from people that have seen these various auroras. I mean, if I could tell my story, I remember one time we were up at a cross-country ski trip staying in a cabin on Gunflint Lake in northern Minnesota, where we could look north over the lake in order to see if there were aurora. And then, of course, in the middle of winter and in the boundary waters, those lakes are totally frozen over. So you can walk out onto the middle of the lake and get the full sky picture of the aurora. And it can be very fantastic that way. And that's really, maybe that's a good note to end on. That's just some of the best auroras I've ever seen have been up there, up north. Yeah.
Well, on behalf of the entire audience, I want to thank you so much for this lecture and sharing your expertise with all of us.
Very welcome.
Thank you very much.